Thank you very much, Marjana. And thanks to the organizers for setting up this meeting in a very nice place. So indeed, I will speak about vortices. So to go along with the theme of the conference, there will be no turbulence, though, in my talk. I want to first thank Vladimir, who has done all the simulations of the results that you will see in this talk. So just to start with the introduction, you have already seen some talks on polariton condensation. So polaritons are photonic, excitonic hybrid quasi-particles that you get when you confine some semiconductor with excitonic transition that is in resonance with a photon that is confined here in this cavity. So because of the finite cavity lifetime, the system will intrinsically be out of equilibrium, so you have to inject some excitations. And basically the injection of excitations you can do in two ways, either resonantly, directly exciting this lower polariton dispersion, or non-resonantly, where you excite higher up and then you wait for relaxation down here. So if you pump the system hard enough under the right conditions, then you will see that you get a build-up in energy at a low energy states. And so when you get this large occupation of the low energy state, you see that you also get a good long-range spatial coherence, so you get a formation of a condensate. This condensate, however, will be not in equilibrium because it's sustained by some driving and there are some emissions. And so actually what I want to discuss today is how this affects the vortex properties, how it affects both single vortex and multi-vortex, so interactions between vortices. So the second way to generate polariton non-equilibrium condensate is the one which is the parametric excitation, which was already explained. And so in this way, again, you get spontaneous symmetry breaking at a different frequency from where you drive. So that's actually the essential part in order to get a free phase and therefore easy creation of vortices, is that you have an emission at a frequency that is not the driving emission. And so vortices have been observed in these polariton condensates. I just show here a few experiments. So this one was in the incoherent driving, this one was in the parametric oscillation case, and you see that by shaping your pump profile of the incoherent drive, you can create some arrays of vortices. So photon condensation, again, I'm not the first one to speak about it, but because I will also discuss vortices in this configuration of photon condensates, I want to briefly introduce them again to remind you. So now instead of putting a material where you have an excitonic transition that you get strong light matter coupling and you get these polariton quasi-particles, you just have weak coupling and you remain with just photons, so non-interacting quasi-particles, and the material that you put is just giving you a thermalization. So by absorption and then some scattering of the matter component with the environment and then re-emission, your photons have some way to know about the temperature of the environment, and so that's the temperature that they will finally acquire. So they follow a very nice textbook Bose-Einstien condensation with the build-up of a condensate, which here you see in energy, in wave number, and here you see it really in real space, because there is some harmonic trapping potential, so the condensation takes place in the ground state, which is much narrower than the thermal width of this condensate. So for the outline of my talk, I will first give you the theoretical framework in which we do the description of these vortices. And then, as I said, I will first go to single vortices, multi-vortices, and in the end, I will discuss also the Kosterlitz-Thouless transition that Marjana already discussed yesterday. But now for a single component, and I will show you some of the analytical or semi-analytical results that we obtained for the transition. So, mean field description, you have already seen the Gross-Pitaevsky equation or nonlinear Schrödinger equation many times. So here, because it's a non-equilibrium system, we have to generalize it. So we have to add a few terms that are related to the feeding of the condensate by these high energy excitations that relax down. So the way that this is modeled is by adding some term, some imaginary part, so that will not be number conserving. The losses, they are very simple. It's just minus I gamma over 2 times psi. And then the gain, that's the opposite of losses. So that's a term with the opposite sign. In order to get a stable solution, you need some equation that says that when you relax down, so when you create a polariton, you lose a higher energy particle. And so that's what this rate equation here expresses. So these are 2 coupled equations that you can solve numerically, but to make contact with other types of equations that have been used before, it's actually useful to simplify this a little bit. So if you say that this reservoir here is in a steady state, then you can solve it with respect to this. You substitute it back and you get a single equation now with some saturable gain that has been used in laser physics before. If you expand it, this expression here, then actually you come to a Gross-Pitaevsky equation with complex coefficients, or if you come from other fields like from superconductivity, you would call it a Ginzburg-Landau equation with complex coefficients. And so this is what people call the complex Ginzburg-Landau equation. And so it has been studied a lot before in other contexts. So for the photon condensation, we also have some theoretical model which is very similar. So differences with the polaritons is that there are no interactions in this case. Similarity is that again there is some imaginary term that describes the absorption of a photon and the re-emission. So that's the terms here, and then of course also the loss term. And then a rate equation that follows the number of excited molecules. And then another term here with this, so it's a kind of loss depending on the energy, and that's the term that will express the temperature of these molecules. So the larger this kappa becomes, the lower the temperature, in combination with this noise term here. So you have a kind of fluctuation dissipation relation between the noise and the friction that then determines the temperature of the system. Okay, so let's have a look at the properties of vortices in this type of equations. And let me just start with some example from the literature. So taken from this paper on the complex Ginzburg-Landau equation that is about 20 years old, I guess. It's a review paper. And so you see that the vortices that you get here, they are not your ordinary vortices. You get some spiral wave formation, and that's directly related to the fact that these are complex coefficients here in this complex Ginzburg-Landau. So these spiral waves, they have a phase profile which is different from your ordinary vortex, where you just encircle the core and having a nice, so the growth of the phase will be on nice circles. Here you will get this kind of spiral wave. And so if you look at currents, you see that there is an outgoing current from the vortex core. What sustains this current is in physical terms, is the driving of the system by this pumping. That's what generates these currents that go out from the vortex cores. If you then translate it into a phase, you get this spiral structure. So in optical systems, theoretically, this has been addressed also quite some time ago. So this is a paper or a book from 2003. And so, maybe the picture is not very clear, but so also here they describe this spiral wave formation of vortices. Then they even cooked up some optical system. It's not directly a laser. You have to play some tricks, and it's actually more, let's say, what we would call it now. It's not a quantum simulation because it's more a classical system. It's, let's say, it's a simulation of a laser where you have access to the system in real time. And actually here they managed to make a nice spiral wave. So we did some simulations for this polariton equation. So in one of the forms, of the reduced forms actually that I have shown you, where you eliminate the reservoir, but you don't expand here this denominator. And so yeah, as you would expect probably, you get a very similar phenomenology. If you make your equation dimensionless, yeah, so you choose as a unit of length the healing length so that the interaction coefficient becomes 1, then basically there is this parameter C which characterizes the non-equilibriumness of the system. So the ratio of the imaginary nonlinearity to the real nonlinearity. And so that's the parameter that will determine how much non-equilibrium your vortex is. If you put it equal to 0, you're back to the ordinary Schrödinger equation, Gross-Pitaevsky equation, and you just get your normal vortices. If you start to increase this parameter, then you will get deformed vortices. So small c, here is the current profile around the vortex. Here is at the larger scales, this is a zoom. So around the vortex core, very close to the vortex core, you mainly see a current that is going around. Then if you zoom out, actually, for the largest non-equilibrium, you really see that the currents, outward currents, dominate. And so it's because there is a density reduction in the core. There you have a bit less losses, but you pump with the same strength. And so the excess particles, they have to be transported outwards. So this is an example that from simulations that we did for photonic condensate. And so maybe here I want to make one remark. It's that normally you would think that for photons, if there are no interactions, then the healing length would become infinite, meaning that the vortex should be as large as the system in which you confine it. So now because we add these gain and losses, we have some other nonlinear mechanism, and so actually there is another way to determine a length scale in the system, and so the vortex core becomes finite. And if this one should be for larger losses, this for smaller losses, so if you reduce the losses, then the size of the vortex core will increase. If you make them equal to 0, yeah, then you are back just to the trivial non-interacting Bose gas without any nonlinearity. So it's not only the structure of the vortex that is modified by the gain and dissipation, but it's also the motion of the vortex. And so again, here I refer back to this work from laser physics, where they call it the restless vortex. So it means that if you start with your vortex at some position, it will not stay at rest with respect to the surrounding superfluid, but it will start moving. And actually, this motion will often be in a kind of circular way. And so the full understanding, and for sure mathematically, I must admit that we are not yet there. So that's maybe one of the things that we could discuss further during this conference. So this one was taken from some simulations for lasers, so complexes Burke-Landau. But when we do it for the photon condensates, which are in a quite different regime, we actually obtain very similar phenomenology. And so you see that your vortex starts to move on this circular trajectory, or sometimes more a circle, but with some drift motion, so it's moving in a certain direction. And then what you see is that there is a core deformation in the direction, so it's elongated in the direction perpendicular to the motion of this vortex. So unfortunately, so far, all the pictures that I'm showing you are only theoretical. So I think it would be nice to have some experimental verifications of these more exotic properties of the single vortices, but that of course requires that you're able to image the vortex even when it's moving, so on the time scale of the system, which of course is pretty challenging in these optical systems. So for polaritons, we had a similar phenomenology. I will not dwell too long on it. So actually, when you put this non-equilibrium parameter quite large, well, equal to 1, so the same as the interactions, see that the vortices can start moving pretty fast, and then they collide with the boundaries like particles, and all kinds of more complicated stuff can happen that I will not go into. I would rather want to move to the multiple vortices that, again, already we heard about yesterday, that when you introduce the non-equilibrium, that you can not only have repulsion between vortices of equal sign, but also repulsion in vortices of different sign. So the way that we looked at this, so Marjana already referred to this paper by Lucas and the group of Sebastian Diel and Ehud Altman, where they found this repulsive contribution to the vortex-antivortex interaction, which is quite unusual because normally you would expect they just attract each other so they can easily recombine. So that's not the case. And so what we did is, without approximations, because this thing is built on quite some approximations, just directly start from this modified Gross-Pitaevsky equation. And indeed, we recover the same phenomenology. So when our non-equilibrium parameter is large, this should be the vortex-vortex interaction energy or potential. It's clearly repulsive, but also the vortex-antivortex is a bit lower, but it's equally repulsive. Then if you reduce this non-equilibrium parameter, as you would expect, you go back to an attraction between the vortex and the antivortex. And then there is some marginal case where indeed you see that at short distances you have attraction, but at long distance here we start to see some hint of repulsion. Our system is finite, so we don't get really to this full asymptotic behavior. So then, when you modify the interaction between vortices, you will also modify the way they move when you put them together. And so the pairs of vortex-antivortex, you would expect them to move them nicely parallel to each other, but you see that now this motion gets deformed, so you get an angle between them in their motion. Vortex-vortex, they should nicely make a circular motion around each other. Again, this circle completely gets deformed due to the non-equilibrium situation. Then, of course, modified interactions also has effects on the recombination. And again, it doesn't seem to matter too much which type of specific model that you use, whether you use this model that we have for polaritons, where we still have interaction between the particles, or we use the photon condensation model. When you start from a vortex-rich state with initial conditions, let's say random, so you have a lot of phase defects in your field, then you evolve it. A lot of them will recombine, so the number of vortices will start to decrease. But then at later times, and for sure when you make the non-equilibrium parameter larger, you will see that quite some of these survive. So they don't manage to find their partner, and even they can form at late times some quite stable complexes with vortices and antivortices present. And so they organize themselves in some configurations that can be stationary, but that can also be just rotating in time. And pretty much similar phenomenology, similar story for the photonic case, where you see that so the trajectories of vortices and antivortices are indicated in different colors, and so they don't feel any tendency to move towards each other, so they just remain moving on their quasi-circular paths. And so at long times you can remain with quite substantial number of vortices and antivortices, depending on parameters. So there are also some regimes where actually in the end parameters go down. So the number of vortices and antivortices go down by a lot. So yeah, this is just a larger picture of the one that was already in the previous transparency to illustrate that some pretty weird vortex anti-vortex configurations can be obtained that are stable for very long times. So I still have 6 minutes, I see, for my last part. That should be fine. So let's now go to a slightly different topic, so not just the properties of a single or two or few more vortices, but really have a look at the phase transition in the system. So again, I can rely on the previous talk. So Marjana already explained you how the phase transition in a two-dimensional superfluid happens by the dissociation of vortex-anti-vortex pairs. So, and the simulations that they did, have been done quite some time ago. And so what we have done is to have a look at this Kosterlitz-Thouless transition again for the incoherently pumped polaritons and for the photon condensates, and I will present here the results that we obtained for the photon condensates. So at first sight, so the BK3 transition, if you visualize it in terms of compass needles, so where the orientation of the arrow is the phase of the system, vortices are some defects in this array of compass needles. So the mapping of a complex field to a phasor model is actually only allowed when you have some argument why the amplitude mode is frozen out, why amplitude fluctuations are not important. And when amplitude fluctuations are important, then actually you reduce to the non-interacting Bose gas. So that's a system which has huge amplitude fluctuations. Martin touched on this when discussing the canonical to grand canonical statistics with very large fluctuations. You go to the system of non-interacting bosons, and there is no Kosterlitz-Thouless phase transition. So what you need is some mechanism, I would say, to first reduce these amplitude fluctuations so that you kind of get your phasors, and then you can have some hope of seeing a Kosterlitz-Thouless-like transition. So in the absence of interactions, this is still possible if your imaginary nonlinearity, so coming from the gain and loss processes, manages to stabilize your density around a certain value. And thinking about a laser where you have some well-defined average photon number, this sounds really plausible, and this is indeed also what happens in this system. And so therefore, even without interactions, we see that you can have this transition from vortex-free to a state with vortices, which obeys pretty much the scalings that you would expect for a Kosterlitz-Thouless transition. So the way we extract the transition temperature or transition point is by analyzing the phase of the field and looking at the appearance of unbound vortices. So in order to identify which one belongs to which phase, what we do is a little time evolution after the generation. So this is just time evolution with the full equations. Then we switch off noise, and bound vortices, they disappear immediately. The unbound vortices, they survive for a much longer time. So this is how we distinguish the two phases so far numerically. And then, so we did a big round of simulations with many different parameters in the system, and kind of the synthesis of our numerical simulations is here in this formula that gives the ratio of the temperature to the hopping strength in the lattice times average photon number. So let me try to make connection to the equilibrium Kosterlitz-Thouless transition. So if you go to equilibrium, then this friction and loss parameter, they cancel. So the loss parameter disappears, the friction parameter cancels here, and what we get here inside this logarithm, at some point in the derivation, you have to introduce some some infrared cutoff. So that's this parameter here that in the non-equilibrium case is somehow related to the losses in the system. So now if we compare this expression to the one by Prokofiev and Svistunov, you see basically the same quantities appearing here. So N, that's the one here, the temperature you see. J, they do it for a continuous system, so that becomes a mass term. And then again a similar logarithm, but now, here's some numerical factor, and here the interaction energy, which gives you or interaction constant, which gives you the infrared cutoff in the interacting case. So actually, our results that we obtain are pretty similar. So what you see now is that actually losses tend to stabilize, so they would enhance the temperature. So actually, they are good for stabilizing the vortex-free case. So then, you can plot this expression for several values of the parameters, and it seems that my time is...
Because for some reason the talks are not homogeneous. So the first two talks have 10 minutes more than the rest of the day. So you have still 10 minutes.
10 minutes, okay, that I will not be able to fill. But, so maybe what I wanted to say about this slide is that the main point of it, maybe that you see here, is that most of the colors here are in the order 1 region. And so if you look at this expression, so basically when it's order 1, that means that your transition temperature is pretty close to what you would expect in equilibrium for weakly interacting bosons. So it's just here in these corners where you would go to extremely small values of your friction that you get strong deviations, but that's actually getting into quite unphysical regimes. So just to illustrate without discussing too much, we did more or less the same exercise for this different equation. And so there we have some different parameters, but again, we followed a similar procedure to extract the critical point for the spontaneous formation of vortices. And so, we have some similar semi-analytics, and so we can plot a critical temperature in a parameter space. So with this, I come to my final slide with the conclusion. So I think I've told you that so the non-equilibrium situation of these photonic condensates affects the single vortex structure, affects interactions between vortices, so therefore also the recombination, and that the Kosterlitz-Thouless transition, as soon as you have gain saturation nonlinearity, also becomes possible without interactions. So I would say for quite some of these aspects, more analytical understanding would be definitely welcome. And so let me not forget to thank especially Vladimir, who has done all the numerical simulations, but then also all the other people of our group of theory of complex and quantum systems at the University of Antwerp. Thank you very much for your attention.
Thank you, Michiel. So are there any questions?
Thank you, Michiel, for that nice run through the history and all these vortices with loss. I wonder why are these vortices, when you have loss, schizophrenic? If you are in an infinite domain and you put it somewhere, they should not know anything about there is no anisotropy of the system. So why they will go in circles, or which part of the circle is actually the vortex going around? So
they do have a direction of rotation.
Right, but if I'm in the domain, how do I know if I'm on top of the circle or the bottom of the circle? It has to be a schizophrenic vortex because it doesn't really know where it is.
How do they start moving in one direction or in...
Not in one direction or the other, but which part of the circle you are. So if I just give you an infinite domain and I give you...
Whether you would start like this,
yes,
Or you would start like
exactly.
this?
And the system is isotropic. So in an isotropic system, you cannot have circles. So the circles must come from something that breaks the symmetry of the system. So these must be boundary conditions. So the circles that you see must be because the vortex, since it has long-range interactions because of the slow decay of the phase, they're filling the boundaries, and that's why they're going in circles. But in an isotropic system, an infinite system, they should not move in a circle.
They should not move in a... So the state that we start from is also not... Yeah, but I see your point of...
Even if you start with something non-isotropic, then it will go on a line, but it cannot go on a circle.
Unless there would be some kind of dynamical instability, and then they choose a...
But again, every time you do the experiment, then you get a different circle in an infinite domain.
Yeah.
So the vortices are schizophrenic. They do not know which way they're going to go.
That's true, but that's indeed a question we did not consider.
We can talk about it. I suspect these are boundary conditions. These are long-range effects that you're feeling the boundaries.
Yeah. Then the question on what would happen in the truly infinite system...
It will not move.
On average, but maybe in a single reality.
You're not breaking the symmetry. If you don't break the symmetry, you cannot move. If I put a billiard ball on a flat table, it should not move.
There are density fluctuations. He's solving the whole model. He's not just solving the phase. You also have amplitude.
No, this wasn't the case where they didn't have the reservoir of the noise. This is indestructible.
In both cases, correct. We see the motion.
So it's not driven by noise. We're talking about a purely non-stochastic system. This is
okay.
a
In the
deterministic
photonic
system.
case, the noise is important. You cannot really eliminate the noise.
But you still saw the circle in the
see it also
deterministic system as well.
The deterministic systems actually, we have to look. There the motion was more straight actually, but so in the laser system, no. It can also be also. It depends on parameters.
Thanks, Michiel. Very nice talk. Can I just ask about the size of the vortex in the photon condensate when G goes to 0? How exactly is it? I understand the argument, okay, it's stabilized somehow, but is there an expression for it? How can I understand it?
So we don't, so the hand-waving argument gives you like number of, so it's on a lattice, so square root of J over gamma gives you roughly the number of sides that is in the core. But that's not to be trusted very quantitatively, but it gives you some idea. Competition between losses.
Hi, Michiel. So nice talk. I just wanted to get your opinion on whether this is of an accurate picture, if the theorists who might want to try and understand how one can formulate a mathematical model for this. So, I mean, would it be accurate to say that for these type of systems, you would have, like if you have a vortex dipole, you would have a contribution that pulls vortices together, you would have a contribution that pushes them parallel, so it has conservative and dissipative dynamics. But in addition, the complication arises from having like a point source sitting on the vortex that gives you a radial flow. Mm-hmm. I mean, is that essentially the three key ingredients you need to capture the physics, or is there some additional thing that you need?
No, I think these are the ingredients. So the repulsive force, the way I understand it, is really coming from the outward flows that are kind of meeting it. But
which you can think of as a point source sitting on the vortex itself.
Yeah, no, this is indeed.
So that's it, you think?
Corresponds to how.
So then there's hope that one can make.
Yeah, I would be definitely interested to discuss.
Yeah, on each vortex. Yeah, of course, yeah.
I also wanted to ask Michiel, so in case of this photonic condensate, which basically there's no real interactions, but in practice there is imaginary interactions. Mm-hmm. But the equations are very similar to the model of Sieberer and Altman. So if they derived forces between vortices, it should be very easy to kind of map it, because the only thing is just changing the real to imaginary part. So one should, by analogy, be able to derive these interactions between vortices. I don't know whether you tried to do that.
So they probably did not have, so they had let's say more this type of single equation. So we,
Yes, but in the language of Gisborne-Landau, it would be just changing the nonlinearity in real part to the nonlinearity in the imaginary.
yeah, so one of the quantitative problems that maybe there is that the molecular dynamics is quite slow, so you cannot really eliminate it. So, but yeah, no, you're
Okay, so you're saying there is no effective single equation theory for
so
for
to go to this single equation, no, yeah, we are still looking at it, but it does not work so well quantitatively to reduce it. Also with the polaritons, you have to take typically a very short exciton reservoir lifetime to make it quantitative, which then experimentally is a bit doubtful. Yeah, so that's a bit situation. No, but if you would put a small lifetime for the excited state, yeah, no, then you're back to that model. Yeah.
Yeah, coming back to the question of Ricardo, do you know if in this experiment, is it an average measurement? Because what the question was if this kind of rotation is stochastic compared.
So there is no.
That you saw the. I didn't get it then.
So
There's kind of optical thing. Yeah, this one, yeah.
yeah, this one.
How do they manage to get the spiral kind of?
We have to look at the details. With some photorefractive oscillator, they do some feedback on the system, so they kind of cheat to get it much slower than what would be the motion of a vortex in real lasers.
Okay, thanks.
Let's thank Michiel again.